Yes, class. So in the last class, we had started with only one circuit we could complete. That was a AC circuit containing only resistor. So in this, both are in the same phase that I told you. So equation also has no phase difference because both are in the same phase, EMF and current. This can be viewed through the phasor diagram and through the graphs also. There can be difference in their amplitude, there can be difference in their magnitudes, but there is no difference in the angles. You can see both are exactly starting from the same angle. Now coming to circuits having only inductors. So see, for inductors, the value of E is this. Now for circuits having only inductors, E is equal to minus L di over dt. This is what we have studied. Right, in induction, self-induction, we have studied E is equal to minus L di over dt. What is E? E is E naught sine omega t is equal to minus L di over dt. So what is di from here? If I just want to describe what is di from here, I can say di will be E naught sine omega t dt divided by L with the minus sign, of course, but I'm not including the minus sign right now. Integration. All right, minus sign will be there though. At the last you can add because that, this is describing you the Lenz law only. All right, so that's why I'm not focusing on that. So total current will be E naught by L. You can take it out common. Sine omega t. I have told you several times it is minus cos omega t divided by omega in integration. So what are we left with? I is equal to minus E naught cos omega t divided by omega L. This is what we are left with. Now see class, one thing, cos theta is equal to sine 90 degree minus theta, correct? Also one thing, sine theta is equal, sine theta, you can always write it as minus theta. So cos theta is equal to sine 90 minus theta, correct? So current we can write it as minus E naught by omega L. Instead of cos omega t, cos theta, what can I write? Sine 90 minus theta. Sine 90 minus omega t. If cos theta is sine 90 minus theta, I can write cos omega t as 90, that is pi by 2 minus omega t. And now look class. Let's shift this minus sign. So if you multiply this minus sign within the bracket, your final answer will be E naught divided by omega L. Sine, this will be shifted because you have multiplied the bracket. Simple mathematics of class 10th, omega t minus pi by 2. If you write it as A minus B, you have to put minus sign. If you write B minus L, you don't. Now look. E naught, if you compare this, I is equal to I naught sine omega t plus minus pi. Fine. Can you see the equation is similar? I naught is E naught by omega L. Omega t here. Phase difference is coming pi by 2. This was absent in case of circuits having only resistors. Why? Because they were in the same phase. So you didn't have anything like pi by 2 or something. So what is the peak value of current ultimately coming? What is the peak value of current ultimately coming? I is equal to E naught divided by omega L. So I is equal to, can you see I is equal to V by R? This is acting like a resistance. So we give it a special term E naught by XL. Omega L is equal to XL. What is XL? Inductive reactance. It's the resistance in the circuit having only inductor. Same work of opposing the moving electrons is being done by the inductive reactance here, whose formula is omega, which is angular frequency, into L, which is self-induction. All right, self-inductance. Or further, you can write omega L as 2 pi nu and this L. This is also valid. Clear? So what is the conclusion? Are they in the same phase or they are in the different phase? You can use both of these statements. See, if you see minus pi by 2 in the formula of current, it is minus pi by 2 means current is lagging behind by pi by 2, 90 degrees. And EMF is leading the current by pi by 2 or 90 degrees. Clear? So you have to remember this in case of circuits having only resistors. When we were talking about circuits having only resistors, their current and EMF both were in the same phase, zero angle between them. But when I say current and EMF, both are different in circuits having inductors. EMF is leading by pi by 2. And see, for inductive reactance, it's the measure of resistance or opposition offered by the inductor to flow of AC circuit. No need to go into the definition. You are already aware of the definition. You know what is resistance? The work of a resistor, the work of resistance is being done by the inductive reactance here in this circuit. And if you look at the formula, no, XL is equal to 2 pi nu L. XL and L, they both are directly proportional to each other. So if you plot the graph, it will be like this. This is inductive reactance. And here you have frequency. This is inductive reactance and this is at frequency. All right. And see class, if suppose inductive reactance becomes 0, so we will say if this occurs, this means it is an ideal inductor. There is no opposition to flow of current. Lots and lots and lots of current will flow. How much current will flow? See, I is equal to E naught divided by XL. If XL is 0, so current will be infinite. Because here 1 by 0 will be infinity. Okay, lastly, the phasor diagrams. Now you will see a difference. See, earlier in case of series having only resistors, they both were overlapping to each other, EMF and current. Now look, EMF is here, current is lagging behind by 90 degrees. Or you can say EMF is leading by 90 degrees. Here look at the graph. Now there is an angle difference also. Earlier there was just a difference in the peak values or the magnitude or the amplitude in resistors. In circuits having only inductors, look, when the current is at 0, EMF has already covered half of its peak value. That is, it has reached its amplitude. Can you see both of them are separated by 90-degree angle? Because current is lagging behind. It is still at 0, EMF is at pi by 2. Understood class? This is what is meant by all the differences which we are studying. Write it down, then we'll see what happens if AC circuit has only capacitor. Okay, class, AC circuit now containing only a capacitor. So this is the same thing. Now you are just having a capacitor. So here voltage V, EMF is E naught sine omega t. Now, if it's the case of capacitor, if it's the case of capacitors, how do we write the charges? Q is equal to CV. That's the formula which we use. Q is equal to CV. So Q is equal to capacitance into V. Voltage is E naught sine omega. All right. Now, if I want to calculate current, this is the equation of charge which I have obtained. If I want to calculate the current, current is dq over dt. Differentiation of charge gives current, right? Learn it in this manner only. Then only you'll be able to remember the derivation. Otherwise, lots and lots of derivations are present in your syllabus. C E naught sine omega t over dt. This we have to differentiate, right? Because I is equal to dq over dt, rate of flow of charges. So I is equal to omega will come out. C, E naught are already constants and this becomes cos omega t. Why not minus and why not getting divided? Because integration is not there. This is differentiation. And in the first, and since the first class of AC, before that even, I have been constantly telling you how to differentiate the trigonometric values. Okay. So, okay, one thing class, see, look here. If I write E naught divided by 1 by omega c, are both the same? This and this. Look here, omega c will go up. So it will be E naught omega c divided by 1. And this is also E naught omega c divided by 1. Are both the same? Can I write this as E naught divided by 1 by omega c, not by omega c. 1 by omega c, because omega c will go up. Both are same. Agreed? Yes or no? Clear till here?
Yes, ma'am. Yes,
Okay.
ma'am.
Okay. So yes, so we are left. And one more thing. Cos omega t, because you know we have to have the phase difference also. So this becomes omega t plus pi by 2. Now class, the derivation part is over. Now comes the comparison part. I is equal to I naught sine omega t plus pi. I naught is this, phase difference is this, omega is this, rest of the things are same. So what we can conclude? We can conclude I is equal to E naught divided by 1 by omega c. It's difficult to use 1 by omega c every time. So we have a term for it, that is xc, which is the capacitive reactance. This is the capacitive reactance. This is the capacitive reactance, which is the resistance of this circuit. So how can we write? Xc is equal to 1 by omega c. XL was equal to omega L, but this is Xc is equal to 1 by omega c. Xc you can write it as 1 by 2 pi nu c also. But main thing, important thing in this equation, current is not minus pi by 2, it is plus pi by 2. It means in these circuits, current leads voltages by 90 degrees. This is the circuit that we have studied. And what is C here? C is the capacitance. All right, so Xc is the capacitive reactance, which is the opposition offered by the capacitor to the flow of AC through it, which is the resistance of the circuit. And in this formula, you can see Xc is equal to 1 by 2 pi nu C. Xc and frequency both are inversely proportional, so you get a hyperbolic curve. And now coming to the graph. Now current is leading. So see, this is ahead of it by 90 degrees. And when the EMF is at it's zero, current now this time has covered pi by 2. So all these things you have to remember. A conclusion is there. IRMS, ERMS will be the same. Concept will be the same. When you are using I naught here for these circuits, use E naught by 1 by omega instead of resistance. If it's not a circuit having only resistors. So normalize using these for this also. Okay, the way you have a habit no, of writing normally V is equal to IR. Start using it for AC also, the way you have been using it for DC. And this is a very short conclusion that I have written, so that if anyone wants to write it down, you can write it down, because that will be helpful in your calculation purpose. Same thing, nothing is different over here. Then the questions part will start, but before that you write this down. See, this says that a pure inductor of 25 millihenry is connected to a source of 220 volt. Find the inductive reactance and RMS value of the current if the frequency is 50 hertz. See, L is given as 25 millihertz, Henry. So this is 25 into 10 to the power minus 3 hertz. So ERMS is 220 volts. Frequency is 50 hertz. We have to find out value of XL, and once you have the value of XL, then we can find out the value of IRMS. XL is equal to omega L, which is 2 pi nu L. This is equal to 2 into 3.14. Frequency is 50. L is 25 into 10 to the power minus 3. All right. So once you will solve this will be, I think, approximately 7.85 ohms. And IRMS. See, you have the value of voltage with you, 220, and you have the value of XL with you. So it will be 220 divided by this value, 7.85. This should be around 28 amperes. These values you can cross-check. Don't rely on these. They can be wrong also. Write it down. Yes, class, this question says a coil has an inductance of 1 Henry. What will be the frequency? Will it have a reactance of 3142 ohms? What should be the capacity of a capacitor which has the same reactance at that frequency? Now see for the first part. L is given as 1 Henry. XL is given as 3142 ohms. So frequency we have to calculate. XL is equal to 2 pi nu L. So from here we have to find out the frequency. Frequency will be 3142. See, XL is this, so it will be XL divided by 2 pi, 3.14 into L is 1. This you can solve. Answer will be 500.31 hertz. This also please cross check. Second part is saying that XC is given as 3142 ohms itself. So what is the value of XC? This is 1 by omega C, which is 1 by 2 pi nu C. All right, this is 1 by 2 pi nu C. So C will be equal to 1 by 2 pi nu XL. So capacitance will be equal to 1 by 2 into 3.14 into 50. XL is 3142. This you can calculate. I think the answer should be 1.013 farad. Please cross check this also. Write it. The next topic is LCR circuits. So in LCR circuits, they are combination of all the three individual circuits of resistors. We have studied individual circuits of inductors. We have studied and individual circuits of capacitors. We have studied. So all the three are combined in this circuit, which we call as the LCR circuit. So in circuits having only resistors, we had seen that V is equal to IR is the formula, and both were in the same phase. And in case of circuits having only inductors, we had seen that the current was lagging by pi by 2. And in capacitors, we had seen current was leading by pi by 2. This was the case which we had studied. Now we'll combine all these three. So when all these three are combined, the phasor diagram looks like this. This is the resistance one, which will be fixed. Inductor and capacitor will be changed. Voltage or due to inductor or capacitor will be changed. How? See, these are phasors. So if these are three phasors, these are vectors, they cannot be just directly added or subtracted. For that, you have to use proper vectors. So if I have this system with me, I have to resolve. I cannot use parallelogram formula or any other formula directly because there are three phases. So I have to solve two first. So I'll solve VL and VC first. So two cases can be there. It can be either VL is greater than VC. So we can write VL minus VC. Right? VL minus VC, which will point out in the direction of VL only. So we'll be just left with VL and VR, then we can use our normal vector laws. But if suppose VC is greater than VL, then we'll write VC minus VL, which will be like this. Downwards VC minus VL. And here we have VR like this. In this case, XL will also be greater than XC. In this case, XC will also be greater than XL. So VR will be there at its place, but this will be VL minus VC here. Whatever will be the angle, the rule will be applied. And if it's VC minus VL, we'll use the opposite one, this one. This is the derivation. Do one thing, write down this first, then we'll see the impedance triangles derivation.